Okay, so this will be the third and last lecture over chapter 7. So in this chapter we get into more of what quantum mechanics really is. Okay, so in the last lecture we made this point that Heisenberg uncertainty principle, so you cannot know both the position and the momentum or speed of an electron. And I forgot to put this on the last one too. Right? Can't know them both simultaneously at the same time. If you know one, then you have no clue what the other really is. But what we can know and what we can calculate, however, is the probability of where you could find an electron at in a region of space using what's known as the Schrodinger Equation. And we're not going to go through the math on how to calculate that because it's extremely complex math. Right, if you have some calculus 1, some calculus 2, some calculus 3, some linear algebra, some differential equations, then you might know enough math to do the math involved in this work. So we're obviously not going to do that. What we're going to do instead, and I'm perfectly okay with that, is just look at nice pretty pictures. Okay, so the probability of where an electron can be found in space is what we call an orbital. So probability means statistics, basically, right? So statistically, where's the greatest shot of, or chance of finding an electron at? So if we plot that, the probability versus the distance from the nucleus. So for hydrogen, then you get a picture that looks like this. And so basically what's done then is to take 90% of this area, take 90% of that region, and we call it an orbital. So the maximum probability of finding hydrogen's one electron is 57 picometers from the nucleus of the atom. Okay, so quantum numbers is basically utilized. It basically provides like an address for where you can find an electron at in an atom. And so there's 4 quantum numbers, so 3 of the quantum numbers, NL and M sub L, are used to describe the different orbitals. And the 4th quantum number, M sub S, is used to describe an electrons in that orbital. So basically they're just like addresses for an electron. Just like if you had an address for your house, so you have a state, you have a town or city, and a street address, and then a house address. Same kind of the similar concept for electrons is what these quantum numbers do, is describe where that electron is at and what the region of space that electron is in looks like. Okay, so we're going to go through these quantum numbers in order, N and then L and then M sub L and then M sub S. And so if you haven't seen this before, the material may not make much sense. It's pretty abstract until we get through N, L, and M sub L. Then at that point we can start tying things together, and hopefully it makes crystal clear sense at that point. But as we go through it, it may not make a whole lot of sense. The material is not difficult. Once you wrap your mind around it, it's really trivial stuff to understand. If you wanted to do the math behind it, that's really complex. But just to understand quantum numbers and the pictures graphically involved is pretty simple. But it's pretty abstract as we go through it. Okay, so N is what's known as the principal quantum number. So it can have values. So for these quantum numbers, you want to know what the possible values are for them. So N can have values from 1, 2, 3, 4, any integer on up to infinity. So it always starts at 1 and can run to infinity. So any whole number greater than 0. So this is the same N that we talked about from the Bohr model. So N primarily describes an orbital's size and its energy, and the energy of the electron in that orbital. So as N goes up, right, the size of the orbital goes up. So we looked at the Bohr model in the last lecture, right? So this is the nucleus of the atom, and then you have shells. And so N represents the different shells. So as N goes up, the size of the shell or orbital goes up, and the energy of the electron goes up. So where is the most stable place to put the electron is in the first shell. So if it's in the second or third shell, then the electron is less stable. So each quantum number has a letter and a number designation. So the first shell, so 1, 2, 3, 4 would be the number designation. They have letter designations as well. 1 is also called the K shell, 2 is called the L shell, 3 the M shell, 4 the N shell, and then it's just following the alphabet. So chemists usually don't use the letter designations for shells. We usually just talk about or say first shell, second shell, third shell, fourth shell, right? So that's all I'm going to expect you to know is just the numerical designation for shells. Okay, so the L quantum number. So it's what's known as the angular momentum quantum number. So what are its possible values? So it can have values from 0 to n-1 and any integer in between. So any whole number or integer in between. So L primarily determines the shape of an orbital, what an orbital looks like. So for its number and letter designations, so its number designation, right, L 0, 1, 2, 3, 4. If it's 0, that's called an s orbital. If L is 1, it's called a p orbital. If L is 2, it's a d orbital. 3 is an f orbital. 4 is a g orbital. This is something that you want to memorize as fast as possible because we use both of these interchangeably all the time. Okay, so again, if L is 0, that means it's an s orbital. If L is 1, that means it's a p orbital that we're talking about. If L is 2, that means it's a d orbital that we're talking about. And so this describes the shape of an orbital. So what does an s orbital look like? Well, s orbitals are spherical. So this is a two-dimensional thing that I'm writing on. You have to keep in mind this is 3 dimensions really. So it's a sphere. It's not a circle, it's a sphere. So if an electron is in an s orbital, then it's somewhere in that sphere, right? Okay, so what do p orbitals look like? P orbitals are dumbbell shaped. So dumbbell shaped, or if we want a nice prettier picture, it looks like this on the right. Where you have to keep in mind that this is 3 dimensions. So the electron is somewhere in that space if it's in a p orbital. So it does not mean the electron traces a path, right? Does not mean it traces some figure 8 path. That's not what it means at all. It just means the electron. This is, if you have the mathematical equation behind this and you plot it, you get these regions of space that look like a dumbbell, and it just means the electron is somewhere in there, right? Where's the nucleus at? The nucleus is here. And of course, the probability of finding the electron density in the nucleus is 0, right? Because protons and neutrons are in the nucleus. So the electron is somewhere in this top lobe or somewhere in this bottom lobe. So sometimes you see, so the nucleus is there. So sometimes you see p orbitals represented simply like this, or sometimes you see them represented like this, where they're shaded. Or sometimes you see them represented like it is here with a phase, plus and minus. So what does that due to? So electrons have wave-like properties. So for a wave, right, you have a positive and a negative phase. And so you could see, to represent that, p orbitals either represented shaded and unshaded lobe, or a positive and a negative lobe, trying to represent the wave-like properties of electrons. But again, it doesn't mean the electron is tracing a path, right? It just means the electron is somewhere in that space. Okay, so if n is 1, so if we're at the first shell, then L can only be 0. So you can only have an s orbital at the first shell. So this will be, put these two together, this will be what's called a 1s orbital. But if n is 2, so keep in mind L can be 0 to n-1, so you always start at 0, and then if n is 2, 2 minus 1 is 1, so L could also be 1. So at the second shell, then you have what are known as 2s orbitals, right? Because if L is 0, that means that's an s orbital. Or at the second shell, L could be 1, and if L is 1, then that means that's a p orbital. Then at the second shell, you have what are called 2p orbitals. So every time you go up a shell, you add a new kind of orbital. The first shell only has s. The second shell has s and p orbitals. So at the third shell, if n is 3, then what are the possible values of L? So L can be 0 to n-1, so 0, or 1, or 3 minus 1 would be 2, so L could be 0, 1, or 2. And so if L is 2, then that means you have d orbitals at the third shell. So here you would have 3 s orbitals, right? This would mean you have 3 p orbitals, and these type of orbitals would be what are called 3d orbitals. Okay, so third quantum number. So it's probably looking a little abstract right now, but we're going to tie it all together in a minute, and hopefully it makes sense. So the third, after we get through this third quantum number, so m sub L is the third quantum number. That's what's known as the magnetic quantum number. And so it primarily determines the number of orbitals of a given shape and their orientation in space. So the possible values of m sub L can be anywhere from negative L to positive L. So the value of m sub L depends on the value of L, right? The value of L depends on the value of n. So if L is 0, then m sub L can only be 0, right? Because it goes from negative L to positive L. If L is 1, so m sub L can be negative 1, or it can be 0, or it can be positive 1, right? All the way from negative L to positive L, all of the integers in between. So if L is 2, then m sub L can be negative 2, negative 1, 0, 1, or positive 2. So some of the questions in this chapter would be that easy. I tell you, L is 2, what is m sub L? And then you would just say, well, it's negative 2, negative 1, 0, 1, or 2. So it may not make much sense. What does that mean yet? But if you can do that, then you got some of the chapter down already. If L is 3, what is m sub L? It's negative 3, negative 2, negative 1, 0, 1, 2, or 3. All the way from negative L to positive L. Okay, so again, so if L is 0, then that's an s orbital, right? Which is a sphere. And spheres only have one orientation in space. But if L is 1, we said if L is 1, then that means this is a p orbital. And p orbitals have dumbbell shape, right? But then m sub L tells you how many p orbitals there are. There are 3 values of m sub L, so there are 3 different p orbitals. And they are orientated differently in space. Right, so if L is 1, m sub L could be negative 1, 0, or 1. That's 3 values, which means there are 3 different p orbitals. So what do they look like? They're orientated differently in space. Right, so I have an XYZ Cartesian coordinate system here. One can be orientated along the y-axis. One is orientated along the x-axis. So again, they're just dumbbells, but they're orientated along different axes. And the other is orientated along the z-axis, right? So we would call this py, we would call this px, and we would call this pz. So 3 orbitals orientated perpendicular to each other, right? This would be a nicer, prettier picture from just a Google search, but you have to keep in mind they're all on the same Cartesian coordinate system. So that's 3 different p orbitals. Right, this in this case they have z up and x that way and y coming in and out. So px, py, pz. 3 different p orbitals. If you had 1 electron, it could be in any of those p orbitals. So we'll see, and I'll make the point, stress the point later, that any one orbital can have 2 electrons in it. So since there's 3 p orbitals, you could put 6 electrons in them. 2 could be in the orbital that's in black, 2 could be in the orbital that's in blue, and 2 could be in the orbital that's in red, right? So you can have anywhere from 0 electrons in p orbitals to 6 maximum, any number in between. Okay, so let's try to put this together. If n is equal to 1, then L can only be equal to 0, right? Because L can only be 0 to n minus 1. And then if L is 0, m sub L can only be 0 because m sub L can only be negative L to positive L. So at the first shell, there is just the 1s orbital. And this is, so the number in front is n, and the letter is L. And so you have to keep them, again, you have to have this memorized. You must memorize this. L is 0 means that's an s orbital. L is 1 means that's a p orbital. L is 2 means that's a d orbital. Okay, so at the first shell you only have an s orbital. If n is 2, so if you're at the second shell, then L could be 0 or L could be 1 because L is 0 to n minus 1. And then if L is 0, m sub L could only be 0. Right? Or if L is 1, m sub L could be negative 1, 0, or positive 1. So what does that mean? So that means at the second shell there is a 2s orbital, so this will be 2s. And there are 3 p orbitals because of the 3 values of m sub L, right? So one of these would be 2py, one of these would be 2pz, and one of these would be 2px. So at the second shell there are 4 orbitals total: 2s, 2px, 2py, 2pz. So what's the difference between a 1s and a 2s orbital? All s orbitals are spherical, right? So if that's 1s, basically 2s, it's a little bit more complicated than this, but for our purposes that's good enough. So 2s is just bigger. So if you went to the third shell and you had a 3s, it's bigger, right? Okay, so the first shell schematic is you only have an s orbital. So you have your nucleus and an s orbital, right? At the second shell, you have your nucleus. That would be your 1s orbital. So if we consider the first and second shell. And then you have a 2s orbital, which is bigger. And then at the second shell, you also have p orbitals. So you have a py, right? And then you have a px orbital. So notice they start at the nucleus, but there's no electron density in the nucleus. So that would be py. And this was that would be px, this was py. So this was px. And then you have pz, right? So you have pz. So again, I'm writing on a 2-dimensional board, but I'm trying to illustrate 3 dimensions. So what does the dotted line mean? That means it's going behind the surface, right? So if you had x and you have y, then you have z that's going in and out. So one lobe is behind the board, or one lobe is behind the iPad that I'm writing on, and one lobe is on the other face of the iPad coming out of the iPad. So this would be PZ. And so the solid wedge means it's coming out towards you. Right, so we've gone from a simple model, chapter 2 model, where you have a nucleus and electron cloud, to the Bohr model, where you have the nucleus and then you have shells. Right, but the first shell is the simple, it's just a sphere, but the second shell is not the simple as the Bohr model illustrates, right? Then we've gone to the quantum mechanics model, where the atom actually looks like that. At the first shell you have a sphere, at the second shell you have a sphere, and you have these 3 p orbitals, a lobe py, lobe px, and lobes in py and pz direction. And that's just the first 2 shells, right? And so every time you go up a shell, you add a whole new kind of orbitals, right? After we go to the third shell, and L could be 2, we did that, right? Maybe not. We're fixing to do that. Okay, so if this was a hydrogen atom where there's just 1 electron, where is that electron at? Well, it wants to be closest to the nucleus. What orbital is closest to the nucleus would be the 1s orbital. It is the smallest and it's the most compact around the nucleus, so it would be in the 1s orbital. And then as you get to multi-electron atoms like sodium with 11 electrons, where is each electron at? And that's what the next chapter is going to cover. Okay, so if n is 3, then L can be 0, 1, or 2, right? because L, again, can be anywhere from 0 to n minus 1. And so again, we get this memorized as fast as possible. So if L is 0, then this is an s orbital, and m sub L can only be 0, so that would be the 3s orbital, right? If L is 1, then these are p orbitals, then m sub L could be -1, 0, or 1. If L is 2, then these are d orbitals, according to this, and m sub L can be -2, -1, 0, 1, or 2, right? So with the third shell, s, p, and d orbitals exist. How many p orbitals are there? 3. P orbitals always come in sets of 3 because m sub L is always -1, 0, or 1. Three numbers, 3 orbitals. Doesn't matter what the shell is. How many d orbitals are there? Well, how many m sub L's are there? Right, L is 2 means d orbitals. M sub L, -2, -1, 0, 1, or 2 is 5 values, so there are 5 d orbitals. D orbitals always come in sets of 5. Doesn't matter what shell it is. Okay, so again, every time you go up a shell, you add a whole new set of orbitals because there's another possible value of L. Okay, so again, at the first shell, you just have 1s. At the second shell, sorry, that's 2s. You have 2s, 2px, 2py, 2pz. At the third shell, you have 3s, 3px, 3py, 3pz, plus these 5 orbitals. So 5d orbitals. So what do d orbitals look like? So let's sketch them. So one of them looks like this. So along the z-axis, you have what looks like a p orbital, and then it has a donut around the middle. That's what's called dz squared. One of them looks like this. It's in the, let's get rid of this to make the picture less convoluted. One's in the xy plane. It's basically a cloverleaf in the xy plane, but it's rotated 45 degrees off the axis. That's what's called dx squared minus y squared. So there's another one that's in the xy plane. Sorry, I just messed up. This one is called 3dxy. It's another cloverleaf, but this time it's orientated along the x and y axis. That's what's called 3dx squared minus y squared. So one of them is a dumbbell with a donut around the middle. The other 4 are clover leaves. They're just orientated along different axes. Okay, so one is in the xz plane. So let me get rid of the x. One is in the yz plane. Again, it's a clover leaf, but it's rotated 45 degrees off of the xz axis, and that's what's called dyz. And then the other one, so let's get rid of y because it's in the xz plane. It's another clover leaf, but it's in the xz plane. So it's like 2 dumbbells squished together to make a clover leaf. And what do you think that one's called? Well, this one's called dxy, 45 degrees off the xy axis, and this is called yz, 45 degrees off the yz axis. This one's called xz, dxz. Or if you Google it, you can get nice, prettier pictures, right? So they just have their XYZ Cartesian coordinate system defined differently, right? But there you have dz squared, right? You can see the dumbbell with a donut around the middle. So the electron can be anywhere in that space. Okay, so I just took this then, and I filled in what these 5 d orbitals are called. Right, dz squared, dxy, dyz, dxz, dx squared minus y squared. So at the first shell, how many orbitals are there? There's 1, and each orbital can only have 2 electrons, so you could put 2 electrons in that orbital. At the second shell, how many orbitals are there? Sorry, there should be 2. 2s, 2px, 2py, 2pz, so there's 4 orbitals. Each could have 2 electrons, so you could put 8 electrons there. So you could put 2 in the 2s, you could put 2 in 2px, 2 in 2py, 2 in 2pz. At the third shell, how many orbitals are there? There's 3s, that's 1. there's 3p orbitals, 3px, 3py, 3pz, so that's 4. And there's 5d orbitals. So 5, 6, 7, 8, 9 total. So there's 9 orbitals. How many electrons? You could put 18 electrons in the third shell. Okay, so we've seen these numbers before. We've seen these numbers in the Bohr model, right? First shell can have 2 electrons, second shell 8 electrons, third shell 18 electrons. So Bohr figured out how many electrons each shell could hold, but he didn't know why, because he didn't understand quantum mechanics yet. But quantum mechanics, it illustrates why. And especially once we have the fourth quantum number m sub s, then it will all tie together. Okay, so if we went to the fourth shell, then L can be 0, 1, 2, or 3, right? So you go to another shell, you add a whole new set of orbitals. If L is 3, what does that mean? That means, again, if we have this memorized, where's that? Right there. If L is 3, that means we have F orbitals as well. Okay, where are we at? Sorry. Yeah, so if L is 3, then m sub L, what are the possible values of m sub L? Then m sub L could be -3, -2, -1, 0, 1, 2, or 3, right? So how many F orbitals are there? There are 7. You see 7 values? So there are 7 F orbitals. How many electrons can they hold? Well, each can hold 2, so you could put 14 electrons there. So we said at the first shell there's 1 orbital, 2 electrons. At the second shell, so that would be the 4s orbital at the, so we're at n equals 4, so there's s, there's p, there's d, and there's f. There's 4s at the fourth shell, there's 4p, and there's 3 of them, which could hold a total of 6 electrons. There's 4d orbitals, right, because of the 5 values of m sub L, if L is equal to 2. So there's 5 of those, right? D orbitals always come in sets of 5, so that could hold 10 electrons. And there's 7 f orbitals, and they could hold 14 electrons. So how many orbitals total? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 orbitals total at the fourth shell. So how many electrons could that hold? Each can hold 2, so 32 electrons, right? So each of these orbitals, basically each of these m sub L values is representing a different orbital that can have 2 electrons in it, right? So again, fourth shell can hold 32 electrons. Okay, so hopefully this is making sense. So what all orbitals exist at the fifth shell? Well, you have 5s, 5p, 5d, 5f, right? So f orbitals exist starting at the fourth shell, and then every shell after that will have f orbitals. And then if we go to the fifth shell, then there must be a new kind of orbital, right? Because if L is 5, if n is 5, then L could go all the way up to 4. So that means you would have g orbitals as well. So just following the alphabet after that. You kind of have to memorize S and P, but D on is just the alphabet, D, F, G, H, so forth. Okay, so then you would also have 5g orbitals at the fifth shell. How many orbitals total in the fifth shell? Well, there's an easy way and a hard way to do this. The harder way would be to work through this, right? All of the m sub L values. Or the easy way is this. The fifth shell can hold 50 electrons. How many orbitals must there be? Well, 50 electrons. So there must be 25 orbitals, right? So there's 1 s, there's 3 p's, right? D's always come in sets of 5. F always come in sets of 7. So how many g orbitals do you think there are? Well, 9, right? There's a pattern, 1, 3, 5, 7, 9. So this is because, so if L is equal to 5, m sub L is equal to -5, -4, -3, -2, -1, 0, 1, 2, or 3. That's 5 values of m sub L, so, or 9 values, so that's 9 g orbitals. And if you add that up, you get 25. Okay, so again, every time you go up a shell, you add a new kind of orbitals. So we looked at s orbitals, p orbitals, we looked at d orbitals. There's always only one of the s, there's always 3 of the p's, there's always 5 of the d's, there's always 7 of the f's, there's always 9 g's. So if we went to 11 orbitals, or h orbitals, there would be 11 of them, right? Okay, so we looked at s orbitals, p orbitals, d orbitals. What do f orbitals look like? And the answer is, I have no idea. I don't have these memorized. I don't deal with f orbitals very often. So, but you can Google it. So I Googled it. Maybe it's in your textbook. If not, you can Google it. So that's what f orbitals look like. 7 of them, much more complex. So I don't know what f orbitals look like. I don't expect you to know what f orbitals look like, but I do expect you to know what s, p, d, and f orbitals look like, and I expect you to know the names of the different orbitals, right? What does dx squared minus y squared look like? What does dz squared look like, for example? Okay, so this is another picture I just Googled. This is probably the best schematic of d orbitals that I've ever seen. So this has all of the d orbitals superimposed on each other. You can see the yellow there is dz squared. Yeah. Okay. So lastly, I meant to put this on the second lecture, but I forgot. So if we go back to the Bohr model right quick, so it's a simple model. It's much too simple, right? Quantum mechanics is what orbitals really look like and what shells really look like. But the Bohr model can be useful to illustrate some concepts in chemistry. So if we just took hydrogen, lithium, sodium, potassium, for example, all group 1 elements, and we sketch the Bohr model. So hydrogen's got 1 electron, so it would be in the first shell. Lithium has 3 electrons, so 2 would be in the first shell and 1 would be in the second shell. Sodium's got 11 electrons, so according to the Bohr model, the first can hold 2, the second can hold 8, third, and according to quantum mechanics, then the third, you only have 1 more to go, so the third would have 1 electron. Or if you went to potassium, right, you could put 2 in the first, 8 in the second, 18 in the third, and then you have 1 in the fourth shell. So if you notice, there's something they all have in common. So they're all group 1 elements. What else do they have in common? If you notice, they have 1 electron. They all have 1 electron in the outer shell. Or if we did this for fluorine, chlorine, bromine, iodine, well, what do they have in common? They're all halogens, right? And if you drew their Bohr model, so fluorine's got 9 electrons, so 2 in the first shell, 7 in the second shell, outer shell. Chlorine, 17 electrons, 2 in the first shell, 8 in the second shell, 7 in the third shell, and the outer shell. Sorry, there should be chlorine, I copy and pasted. And this should be bromine, so 2 in the first shell, 8 in the second shell, 18 in the third shell, and then 7 in the outer shell. So again, what do they have in common? If you look at their outer shell, they all have the same number of electrons, 7 electrons in their outer shell. And so why are elements in columns? Because elements in columns have similar chemical properties, right? Similar physical and chemical properties. And what are chemical and physical properties due to? Well, chemical properties are due to electrons in their outer shell. And so it makes sense then that all of the elements in the same column, same group, have similar outer shell electron configurations, right? Also, what group number is the halogens in? This is group 7, right? This is group 1. 1 electron in the outer shell, 7 electrons in the outer shell. So this is where we can start tying things together in chemistry, right? Elements in the same group have similar chemical and physical properties, and one of the reasons behind that is because they have similar electron configurations in their outer shells, which Bohr model and quantum mechanics nicely illustrates that. Okay, we will stop there, and that is it for chapter 7.